8.3 Lesson 2 Trigonometric Integrals. Our objectives for today are 1. You'll be able to solve trigonometric integrals involving powers of secant and tangent. And 2. You'll be able to solve trigonometric integrals involving sine and cosine products with different angles. So vocabulary, we've seen integration by substitution. We've been using Pythagorean identities and power-reducing formulas. Today we're going to be also using product to sum formulas to help us with an example for Objective 2. But we will begin our lesson by looking at Objective 1, solving trigonometric integrals involving powers of secant and tangent. In your textbook, you'll see these guidelines for evaluating integrals involving secant and tangent. They're good for reference, but as you will see, after you see a few examples, you'll develop an intuition for how to proceed. And if you're not sure, you can come back and take a look at this to get some hints. But it's there for you if you want to refer to it. As we look at our examples today, you also want to remember some basic integration rules that correspond to differentiation formulas. For example, the derivative of tangent x with respect to x is secant squared x. So if you have the indefinite integral of secant squared x dx, the antiderivative would be tangent x. In a similar way, we have the derivative with respect to x of secant x is secant x times tangent x. So if you have the indefinite integral of secant x times tangent x, the antiderivative would be secant x, of course, with a constant of integration. Knowing these differentiation rules will allow us to also know how to do our U-substitutions, because you might, for example, let u be equal to tangent x. Then the differential of u would be secant squared x dx. Or you might let u be equal to secant x. Then the differential of u would be secant x times tangent x dx. Like we saw with our examples in Lesson 1, we will also be using Pythagorean identities to help us rewrite certain portions of our integrand. Today we'll be focusing on this one. You may also need to use this one for some of the problems from the homework for tonight. These are the basic integration formulas from the front cover, from the inside front cover of our textbook. The one thing that I'd like to bring your attention to is rule number 8. If you have the indefinite integral of tangent of u with respect to u, then the antiderivative is negative natural log of the absolute value of cosine of u plus a constant of integration. And here is just to remind you where this particular integration rule comes from. All we do is we rewrite tangent of u using a quotient identity as sine of u over cosine of u. And then we do integration by substitution. Since we already are using u, I'll let theta be equal to cosine of u. Then d theta will be the derivative of cosine of u multiplied by the differential du. And we already have sine of u times du, so we want to isolate that, so multiply both sides of this equation by -1, so we can replace sine u du with -1 d theta, and we can replace cosine u with theta. This allows us to change variables, and of course the antiderivative of 1 over theta with respect to theta is natural log of the absolute value of theta. And then you just replace theta with cosine of u to get this particular integration rule. So if you see the indefinite integral of tangent u du, you know what the antiderivative is. Having gone over the basics, now we're ready to look at some examples. And here's our first example. We have the indefinite integral of tangent x times secant squared x dx. So this problem is easy if you remember that the derivative with respect to x of tangent x is secant squared x. If you remember that, then you can do a U-substitution where you let u be equal to tangent x. Then the differential of u would be secant squared x dx. And since you have secant squared x dx here, you are now able to change variables and integrate with respect to u. So we will have the indefinite integral of tangent of x becomes u, and secant squared x dx becomes du. And this is really easy for us to integrate using the power rule for integration, plus a constant of integration, and we will just replace u with tangent x, and we will have tangent squared x over 2, or 1/2 times tangent squared x plus c. This problem can also be done in another way, and let's take a look at that. In this second way of doing the problem, we can write secant squared x as secant x times secant x, and then we have the factor of tangent x that was there from the beginning. And if we do it this way, then we can let u be equal to secant x. Then the differential of u, the derivative of secant x, is secant x times tangent x. Multiply that by the differential of x. And this would allow us to change variables because we have secant x times tangent x dx, and that would become du. So when we change variables using this substitution, we will have the indefinite integral of u times du. And then we will integrate using the power rule for integration, and our final answer would be this. And both of these are correct. To help you understand that, go back to the Pythagorean identity 1 plus tangent squared x is equal to secant squared x. Notice that tangent squared x and secant squared x, they differ by a constant, because if you add 1 to tangent squared x, that would be equal to secant squared x. And of course, we have our constants of integration here, so I just wanted to help you understand that both answers are acceptable. In this example, we have the indefinite integral of tangent cubed x dx, and we will rewrite this problem as the indefinite integral of tangent squared x times tangent x dx. Now we can rewrite tangent squared x using this Pythagorean identity as secant squared x minus 1. Multiply that by tangent x dx. And I can distribute the tangent x to each of these two terms, and that would give me secant squared x times tangent x minus tangent x dx. And here I have a difference in my integrand, so I can write that as a difference of two integrals. You should remember this integral from our previous example, where the integrand is secant squared x times tangent x. And we've already done that problem, so you can take either of these two answers, whichever you prefer. I'll take the first one. And this one we've also discussed. It is, in fact, rule number 8 from the inside cover of our textbook. So if the integrand is tangent then the antiderivative would be negative 1 times natural log of the absolute value of cosine. So we have this minus sign. So we have minus and then negative natural log of the absolute value of cosine x plus our constant of integration. And then, of course, you have minus negative, which becomes plus. And that's your answer for this problem. Our next example is the definite integral of tangent squared x dx. And what you can do is begin with the Pythagorean identity. So you can write this as the indefinite integral of secant squared x minus 1 using our Pythagorean identity here. Our integrand is a difference, so we can write our problem as a difference of two integrals. And this is an easy problem if you remember that the derivative of tangent x with respect to x is secant squared x. So the indefinite integral of secant squared x with respect to x must be tangent x plus a constant of integration. So we have here tangent x, and then our indefinite integral here with respect to x would be x. So we have minus x plus a constant of integration. Our next example is number 28, the indefinite integral of secant to the 6th power of 3x dx. If you look at guideline 1, if the power of secant is even and positive, in our case we have secant to the 6th power, save a secant squared factor and convert the remaining factors to tangents, then expand and integrate. So we will begin by rewriting this as secant squared 3x times secant squared 3x times secant squared 3x dx. That is, of course, secant to the 6th power of 3x dx. We can rewrite these two factors of secant squared 3x using our Pythagorean identity as 1 plus tangent squared 3x. So secant squared 3x becomes 1 plus tangent squared 3x. And we have that twice. 1 plus tangent squared 3x times 1 plus tangent squared 3x. Because we have two factors of secant squared 3x. The third factor, we want to save that for our integration by substitution so that we can change variables. And what we're going to do is we're going to let u be equal to tangent of 3x. Not tangent squared, but just tangent of 3x. Then the differential of u, the derivative of tangent is secant squared. So the derivative of tangent is secant squared 3x. And then there is an inside function here, so you need to use the chain rule and multiply by the derivative of 3x with respect to x, which is 3. And then you have dx. And of course you have secant squared 3x dx here. So you want to isolate that by multiplying both sides of our equation by 1/3. So you have 1/3 du is equal to secant squared 3x dx. Having done that, we can now change variables from x to u. So we will use our substitution to help us with our change of variables step. So we have 1 plus tangent of 3x is now u, so we have u squared times 1 plus u squared. And then secant squared 3x dx is 1/3 du. And I can write the 1/3 outside, and I have du here. what do I do next? I need to multiply these two factors. And when I multiply these two factors, that gives me 1 plus u squared, which is 2u squared, plus u to the 4th power, du. And now you will just integrate using the power rule for integration, and that would give you 1/3 times the antiderivative of 1 with respect to u is u, and using the power rule for integration, you'll have 2u to the 3rd over 3 plus u to the 5th over 5 plus a constant of integration. And finally, go back to x by replacing every u with tangent of 3x. So we have 1/3 times tangent of 3x plus 2/3 times tangent cubed 3x plus 1/5 times tangent to the 5th power of 3x plus our constant of integration, and that's our final answer. Number 36 is our next example. We have the indefinite integral of tangent to the 5th power of 2x times secant squared 2x dx. All we need to do is let u be equal to tangent of 2x. Then the differential of u will be secant squared 2x dx. And of course we have secant squared 2x dx here, allowing us to change variables using our substitution. So tangent of 2x is u, so we have u to the 5th times du. And once you have done that, you just integrate using the power rule for integration and go back to x by replacing u with tangent of 2x. So you have tangent to the 6th power of 2x, multiply that by 1/6 plus c. In this example, we have the indefinite integral of tangent squared x divided by secant to the 5th power of x dx. And let's take a look at our guidelines. I just want to bring your attention to the very last one here. If none of the first 4 guidelines seem to help, try converting everything to sines and cosines. And that's the approach that we will take with our current example. So if we convert everything to sines and cosines, tangent is sine over cosine. So we have sine squared x over cosine squared x. Divide that by secant is 1 over cosine. So we have 1 over cosine to the 5th power of x. And what you want to do next is to go ahead and do the division. So you have sine squared x over cosine squared x. How do you divide? Multiply by the reciprocal. And we can cancel the common factors of cosine that are in the numerator and the denominator, leaving us with sine squared x times cosine to the 3rd x dx. And this is just a note explaining how I went from here to here. So let's get back to our problem. So by converting the integrand from our problem to sines and cosines, we're able to get to this step, and it becomes like a problem that we did in lesson 1 last week. So what we can do now is the following. We can write cosine cubed as cosine squared times cosine. And then we can use a Pythagorean identity to rewrite cosine squared as 1 minus sine squared. And now we can use U-substitution, where we let u be equal to sine x. So we will let u be equal to sine x, not sine squared, just sine. Then the differential of u will be cosine x dx, and this allows us to change variables. So sine is u, so sine squared would be u squared, and then I have 1 minus, sine is u, so sine squared would be u squared, and then cosine x dx is du. I would need to distribute here, and that gives me the indefinite integral of u squared minus u to the fourth du. And now I can integrate using the power rule for integration, and I will have u to the third over 3 minus u to the fifth over 5 plus c. And finally, I go back to x. My substitution is let u be equal to sine x. So I will replace u with sine x, and I have 1/3 times sine to the third x minus 1/5 times sine to the fifth x plus c. And that's my final answer. Now we'd like to conclude our lesson by taking a look at an example for Objective 2. You'll be able to solve trigonometric integrals involving sine and cosine products with different angles. Our example is the indefinite integral of sine of 3x times cosine of 2x dx. If the angles were the same, we could easily do integration by substitution. For example, if we had cosine of 3x, then we could just let u be equal to sine of 3x. Then the differential of u would be 3 times cosine of 3x dx. And I would have cosine of 3x dx would be replaced by 1/3 du. But that would require me to have the same angle here as I have here, which I do not have. So integration by substitution doesn't work here. Instead, we're going to use a product to sum formula to help us rewrite the integrand. Product to sum formulas are trig identities, and we have 4 variations here. In our integrand, we have the product of sine and cosine. So the first one is sine and sine. The second one is cosine and cosine. And the third one is sine and cosine. So all we have to do is rewrite our integrand using this product to sum formula. So now we will have the indefinite integral of, notice that we have sine of 3x, so u would be equal to 3x, and we have sine of u in our product to sum formula, and cosine of v. So v for us would be 2x. So now we will just rewrite using our product to sum formula so that our integrand will become 1/2 times sine of u plus v, so sine of 3x plus 2x, plus sine of u minus v, 3x minus 2x. And then we have, close the brackets, and we have dx. So the next step would be we can factor out the 1/2, and then we have sine of 3x plus 2x is 5x, so we have sine of 5x, plus sine of 3x minus 2x is 1x. So now we have a sum of 2 trig functions for our integrand. And when you have a sum, you can, of course, integrate term by term. So we'll go ahead and integrate term by term. An antiderivative of sine is negative cosine, but you have to compensate for having the 5x by dividing by 5 or multiplying by 1/5, so that when you find the derivative, you'd be using the chain rule, but you're compensating for that constant of 5 by multiplying by 1/5, so that when you find the derivative here, you would get sine of 5x. And then I have negative cosine x here plus c. And that's my final answer. Today we looked at being able to solve trig integrals involving powers of secant and tangent, and we also looked at solving trig integrals involving sine and cosine products with different angles, and for that we used product to sum formulas to help us rewrite the integrand.